jefe del Gobierno del Reino Unido y jefe de la Oficina de Ciencia y Tecnología, misma que se convirtió en la Oficina de Ciencia e Innovación, seguida de una fusión con el Grupo de Innovación del DTI el 3 de abril de 2006. Antes de este nombramiento, Sir David King fue presidente del Departamento de Química y maestro del Colegio Downing en la Universidad de Cambridge. Es un miembro de Queen's College en la Universidad de Cambridge y continúa siendo el director de investigación en esa misma universidad. Sir David aconseja directamente al primer ministro sobre asuntos científicos. En el 2001 presidió el panel científico sobre enfermedades de la boca y los pies y en el 2003 durante el panel de revisión científica del GM. Preside además otros comités, incluyendo el Comité en Jefe de Recomendaciones Científicas, el Fórum Global de Ciencia e Innovación, codirige la Sociedad de Investigación Energética y el Consejo para la Ciencia y la Tecnología. Del 2004 al 2014 estará profundamente involucrado en la concepción del marco para la ciencia y la tecnología en el Reino Unido. Además, dirige el programa de previsión del gobierno. Se convirtió en miembro de la Sociedad Real en 1991, miembro extranjero de la Academia Americana de Artes y Ciencias en el 2002 y caballero real en el 2003. En el 2006 recibió el cargo de miembro honorario permanente de la Sociedad Real de las Artes. Entre los años 1967 y 2006, Sir David ha ofrecido más de 250 ponencias en conferencias internacionales, simposios, talleres y cursos de verano acerca de sus investigaciones. Ha publicado más de 450 artículos en publicaciones científicas, incluyendo 20 tan solo en el año pasado. Como consejero científico en jefe de su gobierno, ha dado más de 300 ponencias sobre la ciencia en el gobierno en lugares como la Unión Europea, Australia, Estados Unidos, Japón, China, Rusia, Corea, Sudáfrica, India, Brasil, Canadá y Singapur. En el 2002, participó en la 9ª Conferencia de Zuckerman en la Sociedad Real con el tema La ciencia del cambio climático, adaptarse, mitigarlo o ignorarlo. Posteriormente, participó con la Conferencia de Negocios de Greenpeace en 2004 y con la Conferencia sobre la Carta Magna para el Parlamento Australiano en 2005. Sir David publicó el artículo El impacto científico de las naciones en la revista Nature en 2004 y Cambio Climático, la ciencia y la política en el Journal of Applied Ecology en 2005. A la vez, contribuyó a un capítulo sobre la política del cambio climático que fue publicado por la prensa de la Universidad de Oxford.
Thank you very much. I'm absolutely delighted to be here, and I see that here in Mexico you really do things in style. My topic is a broad one, and I intend it to be broad. The environment for a sustainable future has many meanings, and I plan to include several of those meanings. I'm going to actually start with a definition of sustainable development, which was developed by Partha Dasgupta, who previously stood in this room and delivered this lecture, and it just seemed appropriate that I should connect back to the lecture that he gave then. If I could have am I in control of this? Yes. There we go. Sustainable development. So basically, the definition is derived from the Brundtland definition, but what Dasgupta did as an economist was turn it into a quantifiable definition. So he said, each generation, yes, should leave at least as large a productive base for succeeding generations as it inherited from its predecessor. We should leave the planet in as good state as we found it. How do we measure that? Well, he suggests the following. The productive base of any country is essentially composed of a small number of items. Manufactured capital, this could be buildings, hospitals, schools, roads, etc. Human capital, this is the level of education in the country. What is the skills level? And natural and environmental capital. Natural and environmental capital for a country, for example, that has lots of oil or lots of gold, that is environmental capital that you use up. And so, according to the calculation here of the wealth of a nation. As you use it up, if you don't reinvest it into the other areas, you're actually losing the wealth of your nation. So I think, as a matter of fact, that it would be very useful if countries used the Dasgupta parameter for the wealth of a nation in addition to GDP growth. Just focusing on GDP growth means that you lose the opportunity to factor in these important matters, particularly, I would suggest, the matter of the natural and environmental capital, because we have tended to ignore that value in many ways. And of course, one of those is the negative asset associated with emission of greenhouse gases. Now, if we look at this issue of sustainable development, within a single planet, the biggest issue is what is the population going to be as we move through this century that we want to create sustainability around. So I'm going to just deal with the issue of population growth first of all. If I could have the next slide. It's beaten me to it. What we know is that the first billion of people arrived by the year 1800. So that's from the beginning of humanity, 1 billion by 1800. But then this indicates how long it's taken us to develop the second billion, 123 years, the third billion, 33 years, the fourth, until we're now down at 12 years to establish another billion people on our planet. So the population growth has accelerated very dramatically. Now what you do see here is that there is a sign of optimism because the 7th billion is just 1 year longer, the 8th billion up to 16, and we're anticipating the 9 billion at 26. The 8th billion we're very confident about because that's already in the pipeline. So just to point out, there will be 8 billion people on the planet in the year 2028, plus or minus a few. So we're currently 6.4 billion. So there's another 1.6 billion that we're going to have to manage within our limited resources on this planet. And then as we move forward in time, there's further growth. Now, it's just interesting to comment on the dynamics that underlie the growth that we've just seen here. It's important, of course, for countries managing population growth to understand the basis for that growth. And I take on the next slide the classic stages of demographic transition. And what you see here in stage 1 is a steady state between the birth rate and the death rate, both of which are high. So at this level in a typical country, that number, the birth rate, could be measured in terms of female fertility, and that would be round about 7 or 8. That would certainly be true of the United Kingdom if we go back in time. So the average woman would be having 7 or 8 children. So that's the number up there. But the total population is kept down because the death rate, the mortality rate, is high. So in that first stage, we have low population growth. And then in the second stage, and by the way, this works country by country. In the second stage, we introduce improved hygiene conditions, improved medical conditions. Essentially, this is now economic growth occurring off the back of what medicine, engineering, and technology can provide. And in that phase, there's an essential part of this dynamic, because children are still being born at the high birth rate at the beginning of this phase. The death rate plunges down, and so the system goes out of equilibrium. So we have high birth rate continuing. Those people are being born, and all of those women will want children that are born over that period, and so that gives us the rapid growth rate in the second stage, where there's no longer an equilibrium between death rate and birth rate. And then we move in to the third stage, where the two begin to converge. And the reasons for convergence vary from one society to another, or at least the perceived reasons. And I'm going to come to look at how that birth rate is changing currently as we go around the world. Right, so then we finally end up at another steady state, and in that steady state, the birth rate and death rate is equal, and the typical steady state would be a female fertility rate of 2.1. Now, as a matter of fact, this is slightly optimistic from our point of view in Europe, because our birth rate in Europe is now below 2.1. So we have, in terms of our own population, a diminishing population, but we're making that up in terms of immigration. So just to dwell on that point a moment, the female fertility rate in the United Kingdom is currently around 1.8, 1.85. In France is about 2. In Germany, 1.2. And now, and a very recent fall, Italy, Spain, and Portugal, 1.25. The fastest fall in Europe is in those countries. Now, we have to worry about our economic growth when the female fertility rate drops too much, and we have to analyze what is the dynamic that is producing that. But let's just move on to the next slide, where we look at women of childbearing age and fertility. Sorry, this is trends in the population growth. So I just wanted to show this slide to indicate that difference between 12 years and 13 years for a billion actually shows up more clearly when you take 5 yearly snapshots of the additional population on the planet, and you can see that the fall down to from the highest 87 down to 69 is really quite significant. So what we are seeing is the population of our planet is plateauing off. And that process will continue, and we can calculate quite accurately how that will proceed. Now, if I could have the next slide, and we look at this issue of women of childbearing age and fertility. So what you see here on the right-hand side is the children per woman plotted coming down, and we stretch out to 2045, and then we've got the yellow bars are women of childbearing age, so that's women in the 15 to 45 age group, and this is total, so 0.6 billion rising up to 2 billion over that period of time, and that's the dynamic of growth. It's the number of women of childbearing age. There's a tendency, therefore, and I would only say a tendency, for families to produce as many children as will provide 2 surviving children into maturity. And if you're expecting that all of your children are going to survive, then you only have 2. And so that would be the basic dynamic that would explain much of what you're seeing on this. But of course it does vary from country to country and from economic class to economic class. So to have there we see the overall growth split up into the more developed and less developed countries, where you can see that the population in the more developed countries has now stabilized and is coming down slightly, and the population growth worldwide is in the less developed country group. Let me just take a look country by country at what is happening, and again you'll see that this general model seems to work. If I take this slide, we go from Azerbaijan to Brazil to China, countries with totally different policies for containing population growth, and yet this is just to demonstrate that the fall from 1960-65 to the present time is virtually the same in all of these countries. So this sort of indicates that the general model has some validity, and this is then related to economic growth and the improvement of general health conditions. However, I wouldn't want you to think that this is it's as easy as that. Those have been selected as countries with different policies, but which end up in much the same place. And I just point out China. is in the same place as these other countries, despite having the most rigorous policy of all. And the next slide then shows the kind of diversity that exists. So, for example, in the Yemen, the fall is very small indeed. So we've got a big range of diversity here. In Iran, big drop, 7 down to 2.3, and Bangladesh, 6.7 down to 3.5. I think the most important thing to note again, though, is female fertility rates are coming down. The area of the world where we still have relatively high female fertility rates is the continent of Africa, and I'm going to dwell on the issues around the continent of Africa. As the population moves forward to 8 billion by 2028, and what we're suggesting is it'll reach 9 billion by mid-century, and it may or may not exceed that as we move beyond that period. Difficult to forecast beyond 2050, but 9 billion is what we've got a plan for by 2050. So now it's a question of, let's look at the various resources and issues surrounding that expanding global population. So I take the impact on food supply first. Can we feed these 9 billion people? Well, we've had a massive agricultural revolution over the past 20 years with a massive improvement in food provision. If we can sustain that growth in food production around the world, then we can actually provide the food required for that growing population. But there are major issues there. The food isn't all coming in those countries where the population is growing rapidly, far from it. So in fact, what we need is a much more sophisticated way of food aid, whatever, food redistribution than we have today if we're going to actually cope with that part of the problem. So most commentators believe we can feed 9 billion people on our planet, but food aid and trade are going to be a critical part of that process. All right, so if we're going to accommodate this number just by the quarter century, which isn't far away, we will have to increase food production very substantially and improve distribution. Within Africa, population is still increasing at 2.4% per annum. And this really is despite all of the pressures on the African people, the malaria, the AIDS, and so on. So the least developed countries are the ones showing the population growth. 49 of the least developed countries will triple in size over the next 50 years. And that is where the growth is, and that, I suggest, is why the problem is a problem of managing the least developed countries as we move forward through this century. Of course, I think there is also a direct correlation between female education levels and availability of contraception and female fertility rates. So those become key parameters. Let me just dwell for a moment on this question of food distribution. If I take the next slide, we look at net cereal imports in developing countries, and they're grouped into various convenient groupings there. You'll see one of them is South Africa, which is a singularity in Africa, but sub-Saharan Africa, the pale blue, Latin America and Caribbean, the green. What we see is that over the period up to 2015, very massive growth of cereal imports into those countries, and we've got to anticipate a continued growth as we move forward in time. So this just illustrates the point about food aid and trade as a critical part of that process, and that requires politicians in the West to think this through very carefully. Right, so just to give my summary on food, we desperately need more research in this area. We need that green revolution to continue at the remarkably rapid rate that it's gone over the last 20 years. That's a big challenge. we need to invest in sustainable farming. The methodology of farming becomes absolutely critical. Land reform, trade reform will be critical to that process, to create the land where the food can be generated, and then we can feed the 9 billion. So that we seem to be able to manage. Let me just then move on to the impact on health. In terms of maternal mortality and infant mortality, when we have high population growth, we find in any country births to young women, old women, high parity women after short birth intervals occurring. These create real health problems for people having short birth intervals at whatever age and frequent birth intervals. In Indonesia, we find 60% of births had at least one of the 4 major risk factors. That means a major potential health to both mother and child in those situations. And of course, what is also generated in these situations is unsafe abortions. So we are faced with all of these as real issues. Every minute we have 1/2 of the 380 women who get pregnant every minute, they don't plan or wish for the pregnancy. 1/2. 110 women experience a pregnancy complication every minute. 100 women have an abortion, of which 40 are unsafe. 11 people are newly infected with HIV/AIDS every minute. And in addition, we have the problems then, the unmet need for contraception, particularly in developing countries, 10 to 35%, and the number of women dying in childbirth per year, over 500,000. So these problems are continuing with us in terms of the impact on health where population growth is high, and of course, as I've just shown you, that is where the least developed part of the world is. Well, population and poverty have been really centered in the recent past around Africa. I think 30 years ago we would have said India and Africa, and now the change in India has been quite dramatic, and the focus of our attention has moved back over to the African continent. We've got the stresses there that I've already mentioned, the HIV/AIDS, malaria, TB, and the problems this creates in terms of educational levels. I'm going to come back onto that point. Politics, we've got weak governance, corruption, conflict. The problems of Africa are quite massive. Agricultural productivity is not improving. It's going into reverse in Africa. And science and technology is weak, and I want to dwell on this because the basic thesis in the international development community is that science and technology is a luxury for these countries, and I just want to try and deal with that because I believe that is an incorrect position. Let me just, first of all, though, going through the resources that we need for the 9 billion, we come to water. And this graph is a very simple graph, but it contains a very simple truth. That if we assume that freshwater provision is a constant, in other words, the rainfall in toto around the planet is not going to change significantly, but we have this population pressure creating demand for fresh water, but the population pressure also creates polluted water. And so it's the difference between the top curve in red and the yellow curve is the pollution loss. So the available fresh water is the downward falling yellow curve. And of course the concern here is that crossover point in about, according to this, 2045. 2045, this is schematic, plus or minus 10, 15 years. But the point is that there is likely to be a crossover point. unless the problem is managed in a way that we need to manage it better than we are at the moment. If you look at the total world water resource, 12 to 14 million cubic meters, it may sound a lot, but in 1989, we had 9,000 cubic meters of fresh water per person, and by 2025, an easy extrapolation shows us we'll be down to 5,100 per person. So that's the gap narrowing down to the point where each one of us is very close to the limits of the amount of water we need for our survival. And of course, the crossover point that I showed you on the previous graph is optimistic because there's also a distribution issue. We've already seen the disaster in North Africa, Darfur, which is driven by agricultural problems associated with insufficient water in that area. It's crop failures that drive people into desperate actions. And that's what is driving that process, I believe, right now. So the problem is not so much the gross supply of water, but the maldistribution between population distribution and fresh water availability. So once again, we've got a problem that will need to be tackled at the global level. Country by country is going to be a very difficult situation. And now I just come on to infectious diseases. Did I jump one? Can I go back? No. Yes. This is just a map showing the malaria prevalence in Africa, which is a remarkable problem for Africa. One of those great stresses that continent has. Now, the point about infectious diseases is that within our globalized economy, we have created a system where a disease developed in some remote part of the world becomes a problem for all of us. The SARS outbreak indicated the magnitude or the potential magnitude of that problem. Now, we've done a very detailed analysis of infectious diseases in plants, animals, and humans. I was amazed to find that we were unique in bringing together infectious diseases in those three different living communities. And our analysis showed that 80% of human diseases derive from animals. So we actually need to look very carefully at those countries where the juxtaposition of human life and animal life is close. And of course, in Africa and Asia, that tends to be quite predominant. So when we look at the current concern over the avian flu epidemic and the possibility of that developing into a human flu pandemic, which would require the virus to shift from its present state, then that is most likely to occur in remote areas of the world where people are close to the animals that they work with. But we are at risk precisely because with our population movement and dimensions, nobody is sufficiently remote for this not to become a world problem. So infectious diseases is a problem that we all need to combat. And since it's a problem that will predominate in Africa over this century, it brings us back to our responsibilities for that continent. All right, so let's just look at the obstacles to sustainability, and here I'm focusing in particular on Africa. The debt threat, the massive debts that countries were allowed to build up through loans. I'm sure I don't need to emphasize that in Mexico. Aid as a handout. I don't believe that aid as a handout is a proper way to manage poverty reduction. By aid as a handout, I mean, for example, handing food out where there has been a crisis in food production. Fine, you solve today's problem, you do nothing for tomorrow's problem. So that doesn't do anything for poverty eradication. Wealth redistribution, not generation. One of the problems with the aid world is the belief that somehow our economies can have wealth non-redistributed, but the developing world should redistribute its wealth. That's not the way wealth generation occurs. So we need to understand that in our aid processes. Lack of education. There's been a massive focus, both in my country and in the United States, in other aid givers, on primary school education, full stop. The result of that focus is that in Africa, the average class size in primary schools has increased radically. They haven't got a mechanism for producing more teachers. They stopped the massive expansion at primary school level, and they haven't got a mechanism for creating more classes and more schools. They haven't got the infrastructure funds, but the demand from the aid-giving agencies that more and more children should be at primary school leads to one thing, a lowering of the educational standards, even within primary school. So focusing on one aspect of education isn't, and I use the word sustainable again, it's not sustainable. You need to look at education holistically, right the way up to centers of excellence such as this one. Multiple aid agencies. One of the things that freezes up the developing world is having 120, 200 aid agencies which require a large number of civil servants just to manage the requirements from each of those aid agencies. EU and US farm subsidies. Once again, how are we going to manage the issues I was discussing about food distribution and not encourage the developing world to develop food production which we will buy if we protect our own, if we set up trade barriers? And that's exactly what we have at the moment. And then I come back to anti-science and technology attitudes. So let me just work on that one for a moment. I come to the next slide. It was mentioned that I published a paper in Nature on the scientific strength of nations. And this is one of the graphs from that, which is quite a crude measure of scientific strength, but at least it works quite well. This is citation intensity, which I've taken as citation per unit GDP, but you get the same curve roughly if you plot citation per unit population. And so citations to published papers. And then wealth intensity is just GDP per person. And the first thing, of course, is to note, and perhaps not surprisingly, that there is a growth from left to right. Those countries with higher levels of science and technology investment are also countries with a higher wealth base. And this goes back to Das Gupta's definition of the wealth of a nation. We're talking about human capital. And of course, I'm only looking at the pinnacles here. The citations to science are all based on a small number of people in the best university institutions. But nevertheless, that small number of people represent a mass of highly skilled people at all sorts of levels in society. So it is a measure of that process. Now, one of the interesting factors is, sorry, can we have that graph back a moment? I realize I'm going slowly, but the United States appears to be a bit of a strange outlier. The United States investment in the research base looks large when you look at it as a total with a population of 260 million. But when you take it as per person, then the investment in the science base is really not that large. And then the other outlier is Switzerland. There's several reasons for that. Yes, Switzerland, the Swiss government has always believed in investment in science, but there's another reason. It's a relatively small country with a very, very big facility, CERN, and all of the papers that are published from CERN go to the Swiss nation, according to my count. But what is also interesting is the countries that head the table are the small northern European nations. They sit very high. The UK is also a high output nation in terms of research. My function for government is to see that the investment we're making in the science space, and we have doubled it over the last 10 years, and we're now redoubling it again, that the investment we make in the science base is converted into wealth creation. And that is a process that we are moving down the road of. Traditionally, Britain was very good at science, but not very good at innovating from the science base. That situation has changed dramatically in the United Kingdom now. But I want to move back to the general question of sustainability. So let's move on to the point that was raised earlier on, the environment. What are we currently doing to our environment? So here we come on to the topic of climate change, the topic that we've been discussing for the last 4 days. Well, I'm now putting together climate change and poverty eradication as the two challenges. During our G8 presidency last year, the Prime Minister just put 2 items on the agenda, climate change number 1 and African development number 2. Those are the 2 problems, and as a matter of fact, there's a direct connection. The country that is most at risk from climate change impacts, well, the countries are all in Africa. As we move forward in time, the African continent is going to see higher average temperature increases than other parts of the world, and Africa is the area where the cost of adaptation added to all of their other needs means that they're not going to be able to manage adaptation unless there's a massive transformation in poverty eradication rates in that continent. If we look at the problem of climate change, this is a problem that requires a radical global agreed solution. I mean, on Africa, I'm very pleased with the fact that my country has now increased the aid budget to Africa by a very substantial amount over the last few years. It's now £1.2 billion a year. So one country can make a difference in Africa. In terms of climate change, we all have to agree on action. And that's why I believe climate change does represent the biggest challenge that mankind has ever had to face up to collectively. Throughout our history, we have never had to face up collectively to a challenge of this kind before. And so it's a real test of our political systems whether we can get together to manage this problem. Now, it's already been said there are 2 aspects to the problem, mitigation and adaptation. And not all countries are going to be equipped, as I've just said, particularly in relation to Africa, to deal with the impacts of climate change. Let me just take you very quickly, if I may, through the science of climate change. I think we all need to be absolutely clear about the science that underlies this. So if I could have the next slide. Here's the Earth's energy budget. Basically, I'm taking you back to the mathematician Fourier, 1827. Fourier said, I should be able to calculate the average temperature of the planet because I know what's heating it up, it's sunlight. I know what's cooling it down, it's radiation. And since the average temperature of the planet is roughly constant, the amount of heat coming in as sunlight is balanced by the amount of radiation going out. And what he understood was that the radiation going out was very sensitively dependent on the surface temperature of the planet. And so he had a sensitive means of calculating what that temperature was. And he found in his first calculation that the average temperature of the planet was about minus 20 degrees centigrade. Now, being a good mathematician, he decided that what he needed was a fudge factor. And so he introduced one, and the fudge factor is based on this blue stuff, the sky. And so what he said was, some of that radiation is absorbed by the atmosphere, and that atmosphere therefore acts as a greenhouse to the planet. And so the greenhouse effect goes back to Fourier, 1827. So essentially, the atmosphere is absorbing heat and keeping heat in as a blanket. Now, what Fourier understood was daytime, nighttime temperatures in his first calculation, without this atmospheric effect, were enormously different. that was rather like switch off the sunlight and the radiation continues and the planet temperature drops by another 20 degrees centigrade at night. And he knew that wasn't happening. And the effect then disappears when he puts the atmosphere in place, because the atmosphere is acting as a blanket. It keeps the Earth warmer at night. And so with one fudge factor, he gets the average temperature correct, 15 degrees centigrade, and the nighttime-daytime temperature difference is now correct. Now we move forward to British scientist Tyndall. And Tyndall decided that he should try and measure the Fourier factor. So he measures how much of that radiation heat is absorbed by the atmosphere. And being a very careful British scientist, he cleaned up his sample of air first. Absolutely crucial that he did that. And when he measured the heat absorbed, he found it was zero. He found the Fourier factor was zero. So he then repeated the measurement with air as it is. And of course, what he had done when he cleaned up the air was remove the minority gases, carbon dioxide and water vapor. What he was left with was oxygen and nitrogen. They don't absorb in the infrared, and so the Fourier factor was zero for that cleaned up air. So Tyndall had discovered that the minority gases are the greenhouse gases that Fourier was referring to. And when he puts his number in, he finds Fourier was right. His factor matches precisely the factor that Fourier had to assume. And then we move forward again to 1896, and we get to the great Swedish scientist Svante Arrhenius. Now, Svante Arrhenius won a Nobel Prize for chemistry, one of the earliest Nobel Prize winners in chemistry, 1903. But 1896, he sat down to do a calculation. So he was the one who first said, hold on, we're burning fossil fuels at such a rate that we may change the amount of carbon dioxide in the atmosphere quite radically. So he simply said, what if we should double the amount in the atmosphere? What would the average surface temperature go up by? And there he is, 1896, and he concluded 5 degrees centigrade. And the latest models with massive computer power, 5 plus or minus 2. It's not very different. What that means, of course, is the basic physics was understood in the problem. The planetary system in terms of climate is basically understood. There are problems. One of the problems is this little white thing down here on the left, the cloud. How do you handle clouds? Because clouds, we all know that clouds at night assist to keep the warmth in. Clouds in the daytime, if they're white, reflect the light back into space. So clouds can have both effects. Difficult to calculate. Another difficulty to calculate are aerosols. So it's not all been dead easy putting all of the parameters in place. But let me now just show you what has happened to the carbon dioxide levels in our atmosphere. If I could have the next slide. Over the period, I'm taking a period of 60,000 years. We know in detail back now from ice cores, the longest ice core that has been taken from the Antarctic measures 3 kilometers, and basically people are painstakingly determining what that 3 kilometers measures in terms of time scale. It's about 800,000 years. So in other words, at the bottom of the ice core, the snow fell 800,000 years ago, and so you have it within that core, you've encapsulated a historical record of our atmosphere. And from that, just taking the last 60,000 years, you'll see 60,000 years ago we had about 200 parts per million of carbon dioxide in the atmosphere. We come forward to the blue bit, and we emerge through from that ice age into the present warm period. Up it goes to about 260, 270 parts per million. And looking at that rise, we have a temperature rise associated with that of about 5 to 6 degrees centigrade. So bear in mind that's the same temperature rise that was predicted if we double the amount of carbon dioxide in the atmosphere. Now in that transition, we see that the warm period should complete itself if we'd followed all previous warm periods about now, and we should descend into another ice age. However, that is not going to happen. The carbon dioxide level that has actually risen since the industrial period, since the Industrial Revolution, since we started burning fossil fuels and changing land use radically because our population started growing, carbon dioxide level is now 383 parts per million and rising at 2 parts per million per annum. So we know we're going to pass 400 parts per million, and that doubling up to about 560 parts per million is going to happen in a relatively short space of time. Now that's the concern. The second concern is that carbon dioxide level change in our atmosphere, and going back to the Fourier model, this is like putting another blanket on your bed at night. We're covering the planet with another layer of warmth. It's happened so quickly that the planetary system hasn't quite managed to respond to it yet. It's got about 30 years delay. This vast planetary system of ours has an inertia of about 30 years. So that sudden rise means that if we were to stop at 383 parts per million today, the next 30 years of temperature change is still with us. It's still going to be the same. That's an important message because it means we have to prepare, we have to adapt for the changes that are already in the pipeline. Let's just look at how the temperature is changing, next slide, and how the modeling of the temperature change is doing. So what I'm showing here in red are the observed temperature changes since records began back in 1863. And you'll see that the temperature rise is of the order of 0.7 degrees centigrade since the industrial period. Remembering what's in the pipeline, we know that's going to keep driving upwards. And in gray, you see the output of the Hadley Centre model. The Hadley Centre in the UK has set up this enormous computer model to model the changes. And the computer model includes all aspects of atmospheric change, volcanic activity, changes in solar activity, and so on. And you'll see the computer model running backwards in time gives a good representation of the average global temperature change over that period. And moving forward in time, we then have some reliability in the analysis. Now, it was already mentioned, the Kyoto process was 1990, and if you can just look at 1990 on this curve, you'll see that the modelers were predicting the subsequent 16 years of behavior that have already happened with remarkable accuracy. So anyone who questions the model needs to really look at the output of the model and compared with the data that arrived afterwards. So, unfortunately, the science is very robust. At this stage, we have to say the science has been very, very carefully examined. It's very robust. But what this does mean is that we can rely on the science to give us good ideas about how we're going to combat the problem as we move forward in time. Let me just show you on the next slide the way we are emitting carbon dioxide at the moment. Just from carbon dioxide as just one of the greenhouse gases, remember. So we're dramatically increasing the rate of carbon dioxide emission. Why should we worry about this? Well, one of the impacts of this is that as the planet warms up, the oceans warm up, the oceans expand as they warm up, and so sea levels rise. But of course also any ice that is based on land and melts is going to end up in the oceans, and so again, we've got two factors pushing the oceans up. So we have sea levels rising, which means that when we have extreme events, such as storms, such as hurricanes, then these extreme events have much greater impacts than they have in the past. And so, on the next slide, we see an analysis of the number of people flooded annually anticipated by 2080 in the top curve if we just carry on business as usual emitting carbon dioxide as we have been. And that amounts to hundreds of millions of people losing their places of abode, their normal places of abode. 80% of our populations are based on coastline sites. Most of our major cities are on coastline sites. They're the sites at risk. Of course, this is only one of the impacts. I've already mentioned temperature rise is another. The two lower graphs indicate how we might manage to manage the problem downwards, but not eliminate it by introducing new dynamic policies. The sea level rise is going to become unmanageable should we lose, for example, all of the ice from the Greenland ice sheet. If all of the ice from the Greenland ice sheet should melt, sea levels will rise by 6.5 meters. So the Hadley Center attempted to model the melting of the Greenland ice sheet, and you see the output of their model here. And what they were trying to do is to establish the level of carbon dioxide in the atmosphere above which irreversible melting of the Greenland ice sheet would begin. And they concluded that 550 parts per million or thereabouts, and this is about 4 years ago, would be enough to initiate the irreversible melting of Greenland ice. According to their calculation, it would take 3,000 years to complete. Not a very complacent figure, though, because even in a much shorter space of time, you're losing significant ice and sea levels are going up enough to impact around the planet. Now, unfortunately, this model turned out to be very optimistic. The latest satellite data indicate that Greenland is already losing ice at quite a substantial rate. So a beautiful measurement with satellites of the gravitational relaxation of the continent of Greenland as it's losing ice indicates that it's losing 240 cubic kilometers of ice per annum. So Greenland is already losing ice at a tremendous rate, and this does, of course, all end up in the ocean, and so general sea levels rising. We have to manage that process country by country by the adaptation processes we've been talking about. Let's just have a look at the global dimension of the problem in terms of where the carbon dioxide emission is coming from. Now you'll see that the heading up the list is the United States, and if you measure this in terms of carbon dioxide emitted per person, the area of each of those rectangles represents the total carbon dioxide emitted per country. So, for example, if you take a look at India or China, although they're not emitting per person as much because the population is much greater, the total emission from those countries is now becoming quite substantial. But what this means from the point of view of trying to get political agreement on action is that we have a whole range of starting points for different countries. So each country feels its vested interests are represented by taking up a different position in the negotiations. And that, frankly, is a difficult point we're at. When we met here in Mexico, I would say for the first time, we had 19 nations fully agreed, as has already been said, on the science of climate change, on the nature of the problem, of the need for action, and also fully agreed on the economics of climate change as represented by the Stern Review that was presented there, which indicate not only that economically we can manage the problem, but also that if we don't manage the problem, economically we're in for a disaster. So there was general agreement that we have to manage this. But how do you get general agreement around the table when we have such different starting points about managing the problem downwards? That's the real challenge. In the United Kingdom, we decided the way to break the deadlock is to make a unilateral statement. So in 2003, we announced that in Britain we would reduce our carbon dioxide emissions by 60% by 2050, regardless of what happens in negotiations. And we're really looking to other developed countries to follow the lead, and in several of those countries, the French president has announced the intention to reduce emissions by 75%. The German government by 60% by 2060. State of California, 80% by 2050. These are the right statements, I believe, to indicate that we take the problem seriously enough that we are going to begin to take action. By the way, there is a piece of self-interest in this. During the conference, the phrase was, the early bird catches the worm. We believe by getting in early, developing new technologies, we will actually assist our own economy as we see the need for low-carbon energy sources around the world developing. In other words, Denmark has already positioned itself there as a major export of low-carbon technologies, and other countries would like to join them. Now, in the next curve, I just want to stress the major point that at the Kyoto process in 1990, the world was divided up into two parts, the Annex I and the Annex II countries. The Annex I, the developed world, and the Annex II, the rest. And basically, the developed world was told to get on with it and reduce emissions. Now, we in Europe are doing that, but the rest of the developed world has not actually delivered. But nevertheless, let us suppose that we move forward in time on that curve, going conservatively to 550 parts per million ultimate carbon dioxide in the atmosphere. The business as usual scenario is the upward line, carbon dioxide emitted per annum. We want to turn on to global emissions on that downward curve. You'll see that if the Annex I countries all drop to zero by 2045, we'd still have the problem. So the curve would hit the green and then continue to rise upwards. So we need the Annex II nations to be part of this discussion and proposal and agreement. This is not by any means to suggest that we need all countries to be faced up to the same procedures. Not at all. But what we need is discussion around the table which reaches general agreement. Do I have the next slide? Well, I've stressed the point of population growth. I've also stressed the point of education. Let me just underline that, and I'm really focusing my comments very largely on the African continent. The improvement in education in Africa is absolutely vital. That continent at the moment is suffering a net loss of an estimated 100,000 medics, engineers, nurses per annum to the West. Net loss. So their education system is actually being depleted instead of raising standards. We need a massive investment process in education improvements across the African continent. I don't believe the right way forward, for example, is to move in our engineers into African cities and develop clean water and sanitized conditions. The right approach is to generate the educational levels where they have their engineers who will carry that through. That's called sustainable growth. So we need rapid growth in teachers, classrooms, and it does mean that global investment, our investment in those countries, needs to be more focused down those directions. So in conclusion, and my last slide, if we move forward through this century, I think this is the most important issue we face, the general issue of sustainability within a single planet with a growing population. We have a series of problems to tackle, of which climate change is the most difficult at the political level, but there are other challenges that are also extremely difficult. We need to use the wealth and technology that we've developed through the 20th century to turn onto this problem. I think we have become very focused on GDP growth. We've become very focused on being consumer societies. There are other things we live for and should strive for, and I believe creating a sustainable future for our planet is a very good target as we move through this century. Thank you very much.